Now that we know how to tell the difference between a test for independence and a test for homogeneity for portions, namely that a test for independence is one sample where you ask a couple different questions, or ask a question about a couple different categorical variables. And then a test for homogeneity is when you have two or more distinct samples and you ask them a question with several qualitative variable values possible. Then now we want to set up how to run the test. I doubt we'll actually get to the test in this video because to do these tests you have to do a little bit of groundwork. So let's look at this problem. We want to know if money can buy happiness. Is there a relationship between money and happiness? All right, so the following table shows the results related to happiness and family income from the 2008 General Social Survey of a random group of U.S. residents. So first thing we're going to do is we're going to find the marginal frequency distribution. Let's call a spade because that's what it is. All right, so that means if you remember from section 4.4, we want to add up this row and this row and this row. We want to add them all up and we want to find the totals for each row. So let me grab a calculator right here. So I'm going to do clear. So I get that this one right here makes 687. Yep. There you have it. And then I'm going to do that again and again. I'm going to add up all the rest of them. I'll be right back. There, I have all the numbers. So they make, these values right here. And I get the grand total in the corner just to make sure that I did it right. This is a good way to double check yourself. So if you add up the row totals, you'll get a number. And then if you add up the column totals, you'll get another number. And if you did it right, they should make the same number. And they do. All right, so there's the marginal frequency. Lovely. Now we're going to find the conditional distribution for income by happiness. So that means we're going to go by the column variable. So we're going to take each of these values, like 172, divide it by the column total, then 117 and divide it by the column total, and so on. So let me just show you the first one. So we're going to take 172 and we're going to divide it by 315. And we will have 172 divided by 315 gets me about 0.546. All right, I'm going to pause and I'm going to go enter in all these values for the entire table. And I'll be right back. Okay, there I have them all, I'm pretty sure. So I take 383, for example, and divide it by 1089. Then I take 473 and divide it by 1089. I take 132 and divide it by 589, and so on. So I'm working my way down each of these particular columns. That gets me all of those conditional distribution values. All right, now explain why a test of association between these two variables would be a test of independence. Well, it's one group that they asked in 2008, and they're asking them a couple different questions, right? So when it's one group asked two questions about income and happiness, that would be a test of independence. Oops. I know I wasn't spelling that right. There we go. Okay, so now let's see what we have going on here. So independence and dependence. So two categorical variables are independent if the population conditional distribution for one of them is identical in each category to the other. The variables are dependent if the conditional distributions are not identical. So let's look below here. We have income and happiness. Would we say that they are independent or not? So look right here at the not too happy crow. It appears that there is something going on right here, because when you look at this, there's a huge disparity in whether or not you are unhappy. This is unhappy over here, as opposed to very happy over here, right? So when you're not happy, you are much more likely to be average income or below average income, and you're far less likely to be above average income. So above average income, the not too happy crow is very small. it appears that there is something going on there because the disparity in those bars is really, really large. And these are the conditional distribution values that we found. Oh, they would be, except I didn't find these right. Oops, my fault. I'll go fix these. Sorry about that. There we go. Sorry. This is about 0.371. This is about 0.083. And that's why when you look at them, see, there's the 0.371. There's the 0.083. You can see there's this huge disparity. And that would seem to speak to there being some kind of relationship between income level and happiness. So the nicer way to say that is what I just wrote there. So there appears to be a dependent association between income level and happiness because the disparity of the conditional distribution values for the not too happy group is so large. Because that distribution difference is so distinctive, that seems to speak that there is something going on. Now, it's all well and good to say that we expect a certain type of variability there, though. I mean, we don't expect them to be exactly the same, right? So look at these middle ones. Are they far enough apart? Who knows, right? So we know there's going to be some kind of distinctiveness, but the question is, how can we be more certain that there is something going on, that these two variables, income and happiness, are not independent? How can I make sure of that? Not that I could ever be 100% sure, but just to make myself more certain. So to be more certain, of course, we can never be 100% sure. We can never be 100% sure, quote unquote. We would need to conduct a hypothesis test for independence. Independence of the two variables, income and happiness. Now, before we go run that test, we're going to have to learn a couple things. So when you run a chi-square test for independence, it's a test that's used to determine whether there's an association between a row variable and a column variable in a contingency table that's constructed from sample data. So a couple things to note. One, the null hypothesis is always assuming that the two variables are independent of each other. The alternative to that is always assuming, or always stating, not assuming, stating that the two variables are dependent, i.e. not independent, right? So when you're dependent, that means that you are not independent. Okay. Now the degrees of freedom for one of these tests is a little bit different than anything you've ever seen before. It's r minus 1 times c minus 1. That is the degrees of freedom, where r is the number of rows and c is the number of columns. Right? So c is columns, r is rows. That will be your degrees of freedom. All right, then to run the test by hand, you're going to need to figure out the expected cell frequency, i.e. count, expected cell count for each particular cell in the table. And the way to do that is you take your row total times your column total and you divide it by your total sample size. All right, so let's see here. If we assume that these were independent, happiness and family income, what will be expected counts for each of the cells be? So what you do is you take your expected count for it. I got to flip back here real quick to this table right here. This is the one I need. So I need to take my row, 687, times my column, 315, and I divide it by my grand total of 1993, and I find that number. Then I do it again for the next one. I'll take 687 times 1089 and divide it by 1993, and so on. All right, I'm going to type all those up and in this table right here, and I'll be right back. I'm just going to pause or unpause right here and show you the first couple. So 687, that's my row, my first row, times 315, that's my first column, and I divide by the grand total. And that gets me, and I'll show it to you, 687 times 315 divided by 1993, about 108.58. And I'm just going to do this again and again and again. So the next one would be 687 times 1089 divided by 1993. And I get 375.39 approximately. And then I'll do it again. There, and I have 203.03. Now for the next one, I'm going to need 687, or excuse me, not 687 because that's the first row. I need the second row. And the second row's value was 883. So I'm going to take 883 times each of those values that we saw before. So 883 times 315 over 1993 makes 139.56, and so on. There they all are, every last one of them. So for the third row, I had to take the third row's total, which was 423, times it by 315 and divided by the grand total of 1993. And then so on and so forth. All right, that's how to find all the expected value frequencies by hand. So this is what you expect if these two variables were in fact independent of each other. That's what you should get. It's not what you got, of course. What you actually got was back here. These are the numbers you actually got from the table. And the question is, are these numbers so different from the expected numbers that we think that these two variables are not independent? But we'll figure that out in the next video when we go run the test. But before we do that, we need to figure out degrees of freedom. So degrees of freedom is, remember, row minus 1, number of rows minus 1, times number of columns minus 1. Now the number of rows in this table was 1, 2, 3. There's 3 rows. So that'd be 3 take away 1. And the number of columns in this table was 1, 2, 3. Remember, this row or this column doesn't count because that's just the words. So the only ones that matter are the ones with numbers in them. So that's 3. So that would also be 3 take away 1. Now 3 take away 1 is 2. So this is 2 times 2, which is 4. And that would be your degrees of freedom. All right. We now know how to find the expected counts and the degrees of freedom, and we've also reviewed marginal and conditional frequency distributions. So let's stop right there, and then we'll pick up on how to actually run the test in the next video.